In question 1, we're given a polygon of constraints that's shown in the diagram, and then we're given an optimizing function, which is cost equal to $4 times x plus $2 times y. And we're asked to find the minimum cost in this scenario. So the first thing we do is we see we've got 3 vertices. So we'll go ahead and calculate the value of the optimizing function cost at each of those vertices. So we've got cost at vertex A is equal to 4 times 0 plus 2 times 2, which is equal to 4, not surprisingly. Then we look at vertex B, and the cost at vertex B is taking the same approach, this time 4, but we've got decimals, so we're not allowed to use decimals. We want to look then what's the next point we're going to use instead. We're going to go to another point that's in the shaded area, so that's part of the solution set. And we can see we're going to use 1, 3 instead. So we're using 1, 3 rather than 0.8 and 3, 6. So this time it's 4, 1 plus 2 times 3, which is 4 plus 6, which is 10. Then finally, vertex C. Calculate the cost at C. So we've calculated our 3 costs, and we've been asked what is the minimum cost in this scenario, and we see that the minimum cost occurs at vertex 8. So the key point to remember in this situation was that when you're doing your calculations for all of the vertices, you have to make sure you're not using a decimal, but you're using a whole number of values instead. So you go to the nearest point that's still in the shaded area, so still within your polygon of constraints, and use that point to calculate the value instead of exactly the location at B. So there's a minor change. It didn't change the outcome. If we'd calculated using the decimal, it would have been a similar number. It still wouldn't have been the minimum cost in this scenario. For question 2, we've got the polygon of constraints that's shown below, and we've got a series of vertices that go along with that polygon of constraints. The first thing to notice, however, is that we've got a dotted line going across the one side of the polygon. So we know from experience that when we've got a dotted line, that means that points on the dotted line are not considered part of the solution set. So we can't use those in calculating optimum value. So we've given a value statement here, which is 2x plus 10y is equal to the value. And then we're asked to find the maximum value in this scenario. So in order to do that, however, we have to work not with the points that are on the dotted line, but with points that are as close as possible to that dotted line. So we looked at this graph, and we can see that the point 2, 8 is on the dotted line, so the next closest point to it is over 2 up 7. And similarly here, we've got a point 6, 6, and we can instead choose 5, 6 as the points. Now we're going to go ahead and find the value at each of the vertices, but instead of using those 2 points, we're going to use the 2 points inside. So we're going to find the value of the optimizing function at each vertex. We'll start with vertex A, which is 0, 4. And we find the value at A is going to be equal to 2x plus 10y, and then we'll substitute in those x and y values here. So we've got 2 times 0 plus 10 times 4, which of course is equal to 40. Now we look at our second vertex B, but as we've said, we're not going to use 2.8. Instead, we're going to use the next closest point, which is 2, 7. 2, 7 is within the solution set, so we'll use it instead. And the same thing for vertex C, we can't use it, so instead we use 5, 6. So we can see that the maximum value is at closest to vertex B. So we answer the question that was asked, what is the maximum value in this scenario? So we say the maximum value is 70, and it occurs at point 5, 6. So the key message for this question is that when you have a dotted line, points along the dotted line are not part of the solution set, so they can't be used for calculating your maximum value of the optimizing function. So instead you have to go to the next closest point that's within the shaded area, so within the polygon of constraints, and use that in your calculations instead. In question 3, we're asked again, what is the maximum value and how many points maximize this scenario? And they give us an optimizing function here of value equal to 4x plus 8. So again, we've got this time 4 vertices. Step 1 is to go ahead and calculate the value of the optimizing function at each of those vertices. So I'm going to go ahead and do that quickly. So once we've done that calculation, we can see that the maximum value is 72, and it occurs in 2 locations. So there are 2 vertices, A and B, which give us that maximum value. So the 2 points that maximize the value under the given scenario are A and B, and they give us a maximum value of 72. However, we also know that if it occurs at points A and B, it also occurs at every set of whole number coordinates along that line. So in this case, we can look at this line and see it also occurs here, and it also occurs here. So in fact, there are 4 points where that occurs. So I would want to rewrite my message here to say that the max value occurs at 4 points, 2, 8, 4, 7, 6, 6, and 8, 5, and is 72.